Now, exercise of chapter 11. First one, 11.1. Find the maximum frequency and minimum wavelength of X-rays produced by 30 keV electrons. Okay. So here the potential, that is 30 keV, 30 into 10 raised to 3 V. Planck constant, that is 6.6 into 10 raised to minus 34 joule second. Charge of electron 1.6 into 10 raised to minus 19 coulomb. First thing, the maximum frequency of X-rays. So energy E, that is equal to h nu maximum. So nu maximum, that is E by h. But the energy gained by electrons when it is accelerated with the potential difference of V volt, that is EV. So energy, that is EV0 upon h. Substitute the value of E, V0 and h and then solve it. We will get the maximum frequency. Okay. Now the minimum wavelength, that is, now energy, that is given by hc upon lambda also. So when frequency is maximum, obviously the wavelength will be minimum one. So we can write EV0, that is sc upon lambda minimum. So lambda minimum, that is equal to hc upon EV0. Substitute the values of h, c, e and v0. Or directly you can calculate with the help of this maximum frequency also. C, that is lambda into f. So lambda, that is c by f. So if we take the frequency that is maximum one, obviously you will get lambda, that is minimum one. Okay. So using that equation also you can calculate minimum wavelength. Clear to all of you? 11.2. The work function of cesium metal is 2.14 electron volt when light of frequency 6 into 10 raised to 14 hertz is incident on the metal surface. Photoemission of electron occurs. What is the A, maximum kinetic energy of the emitted electrons, B, stopping potential, and C, maximum speed of the emitted photoelectrons? So A, see the frequency nu, that is 6 into 10 raised to 14 hertz. Work function 50, that is 2.14 electron volt. So 2.14 into 1.6 into 10 raised to minus 19 joule. That is given to you. First of all, we have to calculate maximum kinetic energy. Okay. So K maximum, that is half mv maximum square, that is nothing but h nu minus 50. So h 6.6 into 10 raised to minus 34 nu, that is 6 into 10 raised to 14. Minus 50, here substitute the value of 50 in terms of joule and then after solve this one. You will get answer in terms of joule. Then divide that answer, which one is in terms of joule, by 1.6 into 10 raised to minus 19 and you will get the maximum kinetic energy in terms of electron volt. Clear? Then second question, stopping potential. So we know this thing, K maximum, that is EV0. Therefore V0, that is K maximum upon E. Here K maximum, that is 0.343 electron volt upon E cancelled. So that is 0.343 volt. Clear? Then maximum speed. Okay. So here you can calculate maximum speed. By this equation, Einstein's photoelectric equation, here if we make V maximum as a subject, then we can write V maximum that is equal to under root h nu minus 50 into 2 upon m. But this h nu minus 50 that we already calculated. Okay, so substitute that particular value directly here into 2 and divide it by mass of electron 9.1 into 10 raised to minus 31. Then solve it. You will get maximum speed of emitted photoelectrons. Clear to all of you? 11.3. The photoelectric cutoff voltage that is the stopping potential. Okay. In a certain experiment is 1.5 volt. What is the maximum kinetic energy of photoelectrons emitted? Now V0 that is 1.5 volt. Say, we want maximum kinetic energy that is EV0. E into 1.5 volt. Simple answer 1.5 electron volt. Clear? 11.4. Monochromatic light of wavelength 632.8 nanometer is produced by helium-neon laser. The power emitted is 9.42 milliwatt. A. Find the energy and momentum of each photon in the light beam. B. How many photons per second on the average arrive at the target irradiated by this beam? Assume the beam to have uniform cross section which is less than the target area. And C. How fast does a hydrogen atom have to travel in order to have the same momentum as that of photon? See, the given data, lambda that is 632.8 nanometer, 632.8 into 10 raised to minus 9 meter. Power that is 9.42 milliwatt. So 9.42 into 10 raised to minus 3 watt. First of all, we have to calculate energy of each photon. Energy that is equal to HF or H nu, nu that is C by lambda. So we can write energy of each photon that is E equal to HC upon lambda. Substitute the value of H, C and lambda which is given to you. You will get energy in terms of joule. Then divide it by 1.6 into 10 raised to minus 19. Your answer will be 1.96 electron volt. Then after, momentum of each photon. So momentum P that is equal to H by lambda. H that is 6.6 into 10 raised to minus 34 lambda given to you 632.8 into 10 raised to minus 9. Solve this one, you will get the answer. Then B, how many photons per second on the average arrive at a target irradiated by this beam? So here power that is given to you. Power that is nothing but the amount of energy emitted per second. And this energy is suppose made by n photons. So we can write per photon when energy is E. So energy of n photons that is Ne. And when this Ne amount of energy is emitted per second, it implies that itself is the power. So we can write Ne that is power P. So N equal to power upon energy of each photon. Power that is given to you 9.42 into 10 raised to minus 3. And energy of each photon that we calculated 3.14 into 10 raised to minus 19. We will get 3 into 10 raised to 16 number of photons emitted per second. Then third question, see, how fast does a hydrogen atom have to travel in order to have the same momentum as that of photon? Okay, so momentum P, that is mass into velocity. So velocity, that is momentum upon mass of hydrogen. So that is of proton. So momentum of a photon, that we already calculated here, 1.046 into 10 raised to minus 27. Substitute this value of the momentum here. And then mass of hydrogen, that is of proton, 1.66 into 10 raised to minus 27. And then solve it, you will get the answer 0.63 meter per second. Clear to all of you? 11.5. 11.5, the energy flux of sunlight. Energy flux, that is the intensity itself. Energy flux of sunlight reaching the surface of the earth is 1.388 10 raised to 3 watt per meter square. How many photons nearly per square meter are incident on the earth per second? Assume that the photons in the sunlight have an average wavelength of 550 nanometer. Now see, energy flux, that is, I told you, that is intensity. Intensity, that is nothing but the energy per unit area per unit time. Okay. Now, see here, intensity or energy flux, that is 1.388 into 10 raised to 3 watt per meter square given to you. Lambda 550 nanometer. So 550 into 10 raised to minus 9 meter. So energy of the photon in sunlight, that is hc upon lambda. Substitute the value of h, c and lambda. Then solve it, you will get the answer 3.6 into 10 raised to minus 19 joule. So now number of photons incidenting per square meter per second. So number of photons, that is power upon energy, and intensity, that is power upon area. So that is per unit area, and directly here the power per unit area itself is means intensity is given to you. So you can write N equal to 5E upon energy of a photon. So 5E 1.388 into 10 raised to 3 upon 3.6 into 10 raised to minus 19. Solve it. You will get 3.35 into 10 raised to 21 per second. Clear? 11.6. In an experiment on photoelectric effect, the slope of the cutoff voltage versus frequency, it implies that the slope of stopping potential versus frequency of incident light is found to be 4.12 into 10 raised to minus 15 volt per second. Now calculate the value of Planck's constant. Okay. Now we know this thing, in theory we studied the slope of the graph of stopping potential versus frequency, that is h by e. So h by e, that is given to you 4.12 into 10 raised to minus 15 volt per second. Now very simple, h equal to e into slope. E, that is 1.6 into 10 raised to minus 19. Slope is given to you. Solve it, you will get the answer 6.59 into 10 raised to minus 34 joule second. Clear? Next, that is 11.7. A 100-watt sodium lamp radiates energy uniformly in all directions. The lamp is located at the center of a large sphere that absorbs all the sodium light which is incident on it. The wavelength of the sodium light is 589 nanometer. A. What is the energy per photon associated with the sodium light? B. At what rate are the photons delivered to the sphere? So power of lamp, that is 100 watt. Lambda 589 nanometer, so that is 589 into 10 raised to minus 9 meter. Energy of the photon of sodium lamp, that is E equal to Hc upon lambda, this one. Now substitute the value of H, then C and lambda that is given to you, and then solve it. You will get the answer 3.37 into 10 raised to minus 19 joule. Now number of photons per second incidenting on the surface, that is n equal to power upon energy. So 100 upon 3.37 into 10 raised to minus 19. Again solve it, you will get 2.97 into 10 raised to 20 second. Clear? Simple. 11.8. The threshold frequency for a certain metal is 3.3 into 10 raised to 14 Hertz if light of a frequency 8.2 into 10 raised to 14 Hertz is incident on the metal. Predict the cutoff voltage for the photoelectric emission. Simple thing. The threshold frequency nu 0, that is 3.3 into 10 raised to 14 Hertz. The incidenting frequency nu, that is 8.2 into 10 raised to 14 Hertz. Now we have Einstein's equation EV0, which is equal to maximum kinetic energy, that is equal to h nu minus h nu 0. We want to calculate V0. So make V0 as a subject, take E on right hand side. So we can write h into nu minus nu 0 upon E. Substitute the values of h, then nu minus nu 0. From that 10 raised to 14 is taken common. So into bracket 8.2 in minus 3.3 into 10 raised to 14. Divide it by 1.6 into 10 raised to minus 19. Then your answer will be 202.74 volt. Then 11.9. The work function for a certain metal is 4.2 electron volt. Will this metal give photoelectric emission for incident radiation of wavelength 330 nanometer? Now see, lambda, that is 330 nanometer. So that is 330 into 10 raised to minus 9 meter. So we have to calculate the energy of the photons in this radiation. And if energy of this radiation is greater than the work function of the metal, then we will get the photoelectric emission, otherwise not. So let's check this thing. Energy of photons in this radiation, that is Hc upon lambda. Substitute value of H, C upon lambda 330 into 10 raised to minus 9. You will get the answer 6.02 into 10 raised to minus 19 joule. So that is 6.02 into 10 raised to minus 19. Then divide it by 1.6 into 10 raised to minus 19. Your answer will be 3.76 electron volt. But now see, this energy of photons, that is less than the work function of the metal. It implies that when this radiation is incidented on the given metal, photoelectric emission will not be obtained. Clear to all of you? Then 11.10. Light of frequency 7.21 into 10 raised to 14 Hz is incident on a metal surface. Electrons with a maximum speed of 6 into 10 raised to 5 meter per second are ejected from the surface. What is the threshold frequency for photoemission of electrons? Now the frequency nu, that is 7.21 into 10 raised to 14 Hertz. Then maximum speed, that is 6 into 10 raised to 5 meter per second. Okay. Now we want to calculate the threshold frequency. So we have the Einstein's equation, half mv maximum square, that is equal to h nu minus h nu 0. So here make nu 0, this one as a subject. So first take h common, take it on left hand side, and then after make v0 as a subject. So we will get this nu 0, that is nu minus mv maximum square upon 2h. Substitute the values. Nu is given to you 7.21 into 10 raised to 14. Then mass of electron, V maximum is given to you 6 into 10 raised to 5, square of it, divide it by 2 and substitute the value of h and then solve it. You will get the answer 4.74 into 10 raised to 14 Hertz. That is the threshold frequency. Then 11.11. Light of wavelength 488 nanometer is produced by an argon laser which is used in the photoelectric effect. When light from this spectral line is incident on the emitter, the stopping potential of photoelectrons is 0.38 volt. Find the work function of the material from which the emitter is made. Lambda, that is given to you 488 nanometer, so that is 488 into 10 raised to minus 9 meter. Stopping potential, that is 0.38 volt. Now, as per Einstein's equation, we can write the maximum kinetic energy, half mv maximum square, that is equal to h nu minus 50, but h nu that we can write hc by lambda minus 50. So here if we make 50 as a subject, then we can write 50, that is sc upon lambda minus half mv maximum square, but half mv maximum square, that is nothing but ev0. So finally we can write 50, that is sc upon lambda minus ev0. Substitute the values of h, then c upon lambda, that is 488 into 10 raised to minus 9, minus E 1.6 into 10 raised to minus 19 into stopping potential given to you, that is 0.38. Then solve it. You will get 3.46 into 10 raised to minus 19. That is in terms of joule. But always we have to give the answer of work function in terms of electron volt. So divide this one by 1.6 into 10 raised to minus 19. Your answer will be 2.16 electron volt. Clear to all of you? Now next one, 11.12. Calculate the momentum and the Broglie wavelength of the electrons accelerated through the potential difference of 56 volt. Now accelerating voltage, that is given to you. So when electron is accelerated with the potential difference of V volt, the kinetic energy gained by it, that is equal to EV, and kinetic energy, that is given by p square by 2m, that is ev. So we can write momentum p, that is under root 2m ev. Substitute the values. 2 into m, mass of electron 9.1 into 10 raised to minus 31 into e 1.6 into 10 raised to minus 19 into v, that is 56. Solve it, you will get the momentum. Now once we get momentum, then the Broglie wavelength lambda, that is h by p. So here in this equation, substitute h equal to 6.6 into 10 raised to minus 34 upon p, which we already calculated here, 4.04 into 10 raised to minus 24. Solve it, you will get the answer. Clear to all of you? 11.13. What is the momentum, speed, and the Broglie wavelength of an electron with kinetic energy of 120 electron volt? Okay. Now, kinetic energy of accelerated electron, that is half mv square, that is equal to ev. Okay. Now, momentum p, that is equal to under root 2mev. Okay. So when kinetic energy of the electron is 120 electron volt, it implies that it is accelerated with 120 volt. So here substitute the values. 2 e, that is 9.1, sorry, mass of electron, that is 9.1 into 10 raised to minus 31, charge, that is 1.6 into 10 raised to minus 19. It is accelerated with potential difference of 120 volt. Solve it, you will get momentum. Clear? Then after speed, momentum p, that is mass into speed. So speed, that is p by m. P calculated 5.91 into 10 raised to minus 24 upon mass of electron, that is 9.1 into 10 raised to minus 34. Solve it, you will get speed. Then the Broglie wavelength lambda, that is h by p. So lambda, that is substitute value of h upon p, which we already calculated, 5.91 into 10 raised to minus 24. Solve it, you will get lambda. Clear? 11.14. The wavelength of light from the spectral emission line of sodium is 589 nanometer. Find the kinetic energy at which A, an electron, and B, a neutron, would have the same the Broglie wavelength. Okay. Now see, lambda, that is 589 nanometer. So 589 into 10 raised to minus 9. Okay. So here first of all we have to calculate the kinetic energy of an electron. Lambda, that is h by p, but p, that is under root 2m k. Just તમને બતાવ્યું છે અહીંયા બ્રેકેટમાં કે how p is under root 2m k. Clear? So k, the kinetic energy, that is h square upon 2m lambda square. Clear? Now for electron, we can write now kinetic energy of electron equal to h square upon 2 mass of electron into lambda square. Substitute the value of h upon 2 mass of electron, then lambda 589 into 10 raised to minus 9 whole square. Solve it, you will get kinetic energy of electron. Then for a neutron, would have the same the Broglie wavelength. So for neutron, we have to take lambda, same one. Mass of neutron, that is 1.66 into 10 raised to minus 27 kilogram. So as per this first equation, again we can write kinetic energy of neutron, that is h square upon 2 mass of neutron into lambda square. Clear? So substitute the value of h, then take square of it. 2 mass of neutron 1.66 into 10 raised to minus 27 into lambda 589 into 10 raised to minus 9 and take square of it, then solve it. You will get kinetic energy of neutron. Clear to all of you? 11.15. What is the Broglie wavelength of A? A bullet of mass 0.04 kilogram traveling at the speed of 1 kilometer per second. B. A ball of mass 0.06 kilogram moving at a speed of 1 meter per second. And C. A dust particle of mass 1 into 10 raised to minus 9 kilogram drifting with a speed of 2.2 meter per second. Now, we have the equation for the Broglie wavelength lambda, that is h upon mv. Okay. Now, first formulate. Here in this equation, we have to take mass of bullet and speed of bullet. So mass, that is 0.04, speed, that is 1 kilometer per second, that is 10 raised to 3 meter per second. Substitute the values in this equation, lambda equal to h upon mv, you will get lambda. Then in the same equation, substitute mass of ball 0.06 kilogram and speed 1 meter per second, you will get lambda for ball. Then for dust particle, substitute the mass 10 raised to minus 9 kilogram and speed 2.2 meter per second. Again, you will get lambda for it. Clear?